In the last videos, we discussed how to partition the matrices in order to take advantage of the various levels of cache in our memory hierarchy. That involved quite a bit of scribbling and pointing and talking. What we would like to do now is organize all of these insights that we had into something that depicts the algorithm that naturally falls out. Let's have a look at that. So here we depict C being updated by A times B. And first we partition C and B by columns, and you may recall that this was to limit how big of a chunk of B ends up in the L3 cache. So think of this as a loop. Now, for each iteration of that loop, we take our matrix A and our matrix B, and A is partitioned into column panels and B is partitioned into row panels. And recall that to update C now, we need to do the first column panel of A times the first row panel of B, and then the second column panel of A times the second row panel of B, and so forth. Now, that's a loop again. If we now focus on one of those, then we get this picture. And now what we do is we take our matrices C and A, and we partition C into row panels and A into blocks. And then each row panel of C is updated by doing the corresponding block of A times the row panel of B. And therefore that row panel of B is actually used multiple times, and we would expect that to end up in the L3 cache. So if we now focus on one of those block times row panel multiplications, that itself can again be done as a loop. And what we do there is we take our matrix B and we partition it into micropanels, and we take our matrix C and we partition it into micropanels. And then each of those micropanels of C is updated by doing a block of A times the micropanel of B to update the micropanel of C. Now notice that in this loop, the block of A gets reused multiple times, and therefore that block of A you would expect to end up in some cache. And what we noticed before was that we want to size that block of A so that it fits in the L2 cache. If we now look at one of those block times micropanel multiplies, we remember that we will want to orchestrate this by partitioning the block of A into micropanels, little row panels, and partitioning the micropanel of C into microtiles and looping over those. And notice now that that micropanel of B is reused multiple times, once for each of the micropanels of the block of A, and therefore we would like to keep that in one of the caches, and it's conveniently sized so that it can remain in the L1 cache. So if we now look at what happens during one iteration of those loops, we end up with the micro-kernel. Okay, we have a microtile of C, which we park in the registers, and then we update that microtile by looping over the micropanel of A and the micropanel of B and performing rank 1 updates. And for each of those rank 1 updates, we then bring a column of A and actually only one element of B into registers. So here's the complete picture.